Welcome to the Hardware Design Flow for Altera SoC online training. This is a high-level training focused on the hardware design methodology needed to create an embedded system with our SoC devices. Feel free to pause, move forward, or go back as you need in this training. You will find a list of resources and links at the end of this presentation, or go to the resources section at the top. Let's get started. These are the topics for this training. First, we'll give an overview of SoC devices, discussing the components and the system design flow. As part of the hardware design flow topics, we'll discuss Quartus software and platform designer tools, including instantiating the hard processor system, or HPS, and bringing custom components into the environment. In the SoC hardware debug section, we'll discuss the features from Platform Designer that make simulation easy, as well as on-chip component debug options. Lastly, an overview of the ARM Development Studio and Ashling risk-free IDE for Altera FPGAs software for debugging will be covered. Go to the resource section to learn how to obtain all the software needed from our websites. Let's move on to an example of system-on-chip overview. For a typical system development, here are all of the components. At the very bottom, the system's foundation is the hardware or silicon devices. Within those devices are IP cores that perform a particular function. On top of that, there's the control and status register view of those components. Crossing into the software domain, we may see the bootloader development and driver development for a particular IP component. Above that, there's an operating system, middleware such as Ethernet stacks, and the user application software sits at the very top of the development layers. For this presentation, which is meant for FPGA engineers, we'll focus on the bottom three layers, the devices in which IPs are implemented, the IPs themselves, including soft IP in the FPGA, and the register view to allow the lowest level of software access. Here's the system development flow. Since this is the hardware development flow training, the objective is to learn about the features in the left column. Altera provides tools necessary to carry out software development, covered in separate online training and resources. On the hardware side, we start with the Quartus Prime software design software, which is used to synthesize, then place, and route RTL source files. The Platform Designer system integration tool generates the RTL sources. It is a front-end tool that allows you to bring together various IPs together quickly and automatically generate synthesizable interconnects. Once the hardware system is created for testing it and functionally simulating it, the bus functional models supported by the Platform Designer system will make that easy. For IP verification, you can use FPGA tools such as Signal Tap Embedded Logic Analyzer or System Console. Those tools can also be used for an SoC development environment as you normally would in an FPGA system. Finally, once everything is ready, the FPGA hardware needs to be programmed and ready for release to make the software design flow go easy. Platform Designer system integration tools used to bring the hard processor system together with other components will generate handoff files. This is a more detailed block diagram of the Agilex 5 SoC FPGA device. The hard processor system HPS contains the dual-core ARM Cortex A76 and a dual-core ARM Cortex A55 ARM Dynamic Shared Unit DSU. The L2 memory interface of each core is internally connected to the DSU L3 memory system via CPU bridges. Also available, a rich set of peripherals, including Ethernet ports, 2 USB on-the-go ports, 2.0 and 3.1, interfaces to flash memory, general-purpose embedded peripherals such as UART, SPI, and I2C, and I3C, and a shared multi-port front-end SDRAM controller that supports DDR4 and DDR5 with ECC. The Agilex 5 SoC FPGA includes a secure device manager. The SDM helps ensure data integrity and facilitates secure boot, configuration, and operation of the device. As you're going through this training, as an FPGA designer, you should find the hardware portion very similar to the traditional methodology. FPGA engineers can feel comfortable that the normal FPGA flow and design is the same as it has always been. The integrated hard processor core will have no impact on their normal FPGA environment. So all the usual development and debugging tools are still available. Similarly, for ARM software engineers, the typical environment that you are used to is the same environment you will use to develop for the Altera SoC. It should be transparent to you as if it were two separate chips. The hard processor system includes more than just the processors. Here is a list of the prominent components. The multiprocessor unit features dual ARM Cortex-A76 and dual ARM Cortex-A55 processors, Ethernet controllers from Synopsys, multiple flash interfaces, and serial interfaces including USB, SPI, I2C, I3C, and USB 3.1, among others. There are also UARTs and GPIO interfaces in the HPS. You can find more information on the resources available from this and other Altera SoC FPGAs at the end of this presentation. Now that we've seen an example of an SoC device, let's dive into the hardware design flow. First, we will examine Quartus software and platform designer tool flows, including HPS component instantiation and custom components that the hard processor system interacts with. This is the complete Quartus Prime software and platform designer hardware design flow for use with the SoC devices. On a high level, you start with a Quartus Prime project or open an existing one. Then, within the project, create a QSys system that instantiates the HPS, custom IP inside Platform Designer, and other off-the-shelf IP available from Altera or third-party vendors. Generate the system, which will create simulatable or synthesizable HDL versions of the system depending on the generation options. Software handoffs generated will go to the firmware engineer. From that point, you can functionally simulate or include the generated QSys system in the Quartus Prime project. In Quartus software main window, run analysis and elaboration to allow the tool to understand the hierarchy of the design. Then create I/O assignments using a script generated by Platform Designer and manually set I/O assignments for other general-purpose FPGA I/Os, and finally run a full compile. Once an FPGA programming bitstream is completed, you'll be able to perform hardware verification before product release. The Golden Hardware Reference Design, or GHRT, is a reference design for Altera SoC FPGAs developed and maintained as part of a complete solution to boot to embedded OS and application inside a Golden System Reference Design. The GHRD provides a reference design that demonstrates the system integration between the HPS and FPGA IPs. For further information, you can go to the GitHub repository provided in the resources or to rocketboards.org. As we said earlier, the first step in the flow is to create or open a Quartus Prime software project. The easiest way to do this is to use the New Project wizard. A Quartus Prime software project is simply a collection of all source files and settings regarding a particular design. When creating the project for use with the SoC device, make sure to select a family that contains the hard processor system. There are several families and subfamilies that include the HPS. Once the SoC project is created, you are required to use the Platform Designer System Integration tool to instantiate and connect the HPS and other relevant components. From the Project Navigator, you can open a QSys file, and it will open in Platform Designer or open Platform Designer from the Tools menu to create a new QSys file. The Platform Designer System Integration tool saves significant time and effort in the FPGA design process by automatically generating interconnect logic to connect intellectual property, IP, functions, and subsystems. It significantly simplifies the process of generating a system. The idea is to have all components, including custom ones, conform to a standard interface, such as Avalon or AXI, and since Platform Designer understands these interfaces, it can automatically generate the interconnect for those components and interfaces. You can use the tool to quickly integrate IP, author custom IP, and verify the components or system using standard simulation or on-chip methods, or work on an existing project. Under the hood, Platform Designer uses an FPGA-optimized network-on-a-chip (NOC) technology, delivering higher performance, more scalable solutions. This window shows what the Platform Designer tool looks like. From the IP catalog, you can add various IP, including the HPS or custom IP. In the System View tab, you can make the appropriate connections to and from compatible interfaces. Once you're done, go to the Generation HDL button to generate the appropriate HDL and other supporting files related to the system. In the Platform Designer tools, the component library lists all available IP and subsystems that are available and can add it to your current Platform Designer system. Off-the-shelf IP are listed under the Library section and subsystems are listed under the Project section. Any custom IP or components available will also be under the Project section. The IP catalog is organized by categories to make it easier to find the IP you need. Just expand the category and possibly subcategories and highlight the component that you want to add to your system. To add a component to your system, double-click on the component name or click on the Add button with the component highlighted. You can also use the search field to filter the component library by name. Just start typing in characters, and Platform Designer dynamically filters the list as you type. The screen capture shows the hard processor system component, which is located inside the Embedded Processors folder of the component pick list. Platform Designer is a GUI-based system integration tool for system design that enables design reuse and simplifies complex system development. If you want to learn more about using Platform Designer, you can take a look at the e-learnings available and visit the resource section. Now let's take a look at HPS component instantiation. These sections are focused on the parameters on the hard processor system for Agilex 5 FPGA IP parameters and configuration. This is the main window for configuration for the IP. You can see at the top a section that separates each category for settings. Then each section has individual settings selections, and at the bottom the messages, info, errors, and warnings dialog box that changes dynamically as you go configuring everything. The hard processor system components are fixed, but the operations are configurable. When we configure the HPS, most of the options are regarding the interfaces. The first tab of the HPS configuration is related to the interface to and from the FPGA. In the General section, you can enable options that can send events to and from the FPGA, direct the GPIOs to and from the FPGA, enable boot signals from the FPGA, and allow the connection of debug interfaces. On this tab, you can configure the bridges that connect to the FPGA side and specify the options for the primary interfaces between the FPGA and HPS. This is a continuation of the configuration in the FPGA Interfaces tab. Here you can set up the signals exposed to the FPGA design from the HPS. In the DNA Peripheral Request section, you can enable up to 8 peripheral request signals to allow the FPGA components to request DNA transfers. Lastly, you can enable peripheral interrupts to and from the FPGA to the HPS. The technical reference manual for each family gives mappings from signals to GIC interrupt numbers. This group of tabs is for setup for input clocks, internal clocks, and output clocks, and resets. Some of the configurations for this section are added into these files as needed. SDC file generated by Platform Designer. Handoff binary for the FSBL. This tab contains the configuration for the external clocks, FPGA to HPS clocks, and peripheral clocks. The peripheral clock configuration section specifies the clock frequencies for enabled peripherals and the ones set to be routed to the FPGA. The tab inside HPS clocks for PLL clocks can help you set the frequency of each clock for each HPS peripheral, set the source of clocks for the PLLs, set up clocks from HPS to FPGA. In the Power and Resets tab, you can enable the FPGA signals to reset the HPS, enable the HPS signals to reset the FPGA, and enable reset to be caused by the watchdog timer. For Agilex 5 SoC FPGA, the SDRAM needs to be added as a separate Platform Designer component to be connected to the HPS. In the IP catalog, you can type External Memory Interfaces for HPS, followed by the family name to add the component. Then connect exposed signals to the corresponding SDRAM IP block signals. If you want to learn more, you can go to the e-learning link provided in the resources section about memory interfaces. The I/O interface also needs to be set. On the Peripheral Pin tab, you can implement the pin set assignments for specific peripherals. In this tab, peripheral interfaces are enabled, and in some cases modes of the peripheral can be selected. Each peripheral goes to at least one pin mux. The pin muxes are controlled by selecting a specific HPS I/O set. Choosing an I/O set determines which I/O pins will be used for this interface. For more details on which pins can be used for a specific peripheral, please see the pin connection guidelines for the various SoC devices. This tab allows fine-tune pin settings for pin mux exposure to the FPGA design. The Advanced IP Placement tab allows you to be more specific about the placement of each peripheral pin in the HPS dedicated I/O quadrant space. Each location has a pull-down selection menu where you can select which peripheral I/O to be routed to the pin location. The Advanced FPGA Placement tab allows you to route specific peripherals to the FPGA. This is a general look at an example of how the HPS component is added to the system in the GHRD. Once the components are instantiated in the System Contents tab, you can make the connection to and from appropriate interfaces in one of two main ways. First, you can use the Connections column. Here, compatible connections are shown in gray with a circle. Clicking on a hollow circle will darken the connection, which indicates a particular set of interfaces is connected. When you have a lot of components, it may be difficult to find the correct connections. In this case, you can consider right-clicking on a particular interface, which will show you a set of possible connections, and you can choose to connect from there. Once you finish configuring the HPS system, you'll be able to generate the appropriate HDL files for the system. Depending on the options you choose, you can generate for simulation, test bench, or synthesis in either Verilog or VHDL. The outputs will be located in the appropriate directory, in addition to the HDL for the system and the interconnect. When you generate, you also generate software handoff files used by the software debugger or Linux device tree input. Settings for hardware compilation can be done from the Assignments option, then Device and Pin options. Some of the most important configurations to be set in this option are the clock source and configuration scheme. For more information about these options, refer to the Device Configuration User Guide. Agilex 5, FPGAs, and SoC or any other family you are working with. The configuration option for HPS Debug Access Port allows the HPS JTAG port to be connected to HPS pins, SDM pins, or disabled for a JTAG debugging connection. Here we see the different files generated by Platform Designer and Quartus Prime software project compilation and how they are used by the software tools. First, Quartus Prime software generates the SoC FPGA bitstream used to configure the FPGA portion of the SoC. It contains HPS I/O configuration data and FPGA I/O configuration. The SoC file also contains the handoff data for SDM firmware and for the HPS first stage bootloader. Both are used to pass parameters for SDM and HPS FSBL. For software purposes, a handoff directory is created for use by the second stage bootloader generator, which creates the software source files necessary to configure the clocks, I/O pin MUX, and configure the SDRAM via either software or FPGA image depending on the device and family. The SVD file is a description of soft IP peripheral registers in the FPGA. This can be used in a similar fashion as symbol files in the software debugger, giving you access to the hardware registers directly from the ARM software debugger. Each individual FPGA peripheral, whether custom or off-the-shelf, would need to have an SVD file that gets aggregated when Platform Designer generation happens. Lastly, the SOPC info file output of Platform Designer is used by the device tree generator. The device tree standard specifies hardware connectivity so that the OS kernel can load those drivers without rebuilding the kernel. This makes the system flexible regarding the changing FPGA hardware available. The SOPC info file can also be used by the system header file generation tool to create the .h files, which contain macros that represent the FPGA Platform Designer system. Now that we understand basic Quartus Prime software and Platform Designer tools, including the HPS component, let's take a look at how to implement custom components in the FPGA that interact with the HPS. Platform Designer can integrate different components together, but the components need to conform to one of the supported standard interface. There are many advantages of conforming your custom IP to a standard interface. This ensures compatibility with other components, makes design entry easy by using the tools such as Platform Designer, and it makes it very easy to verify. This includes Avalon memory mapped interfaces, where there's a host requesting reads and writes from an agent. There's Avalon streaming, which is meant for point-to-point high-throughput application, and there are many ARM AMBA interfaces including AXI3, AXI4, AxiLite, and Stream, as well as APB. If your custom component conforms to one of these standards, your component can be seamlessly integrated with other IP by the Platform Designer tools. Before conforming to a specific interface standard, it's important to understand the interface completely, and this can be done by reading the specifications published by Altera or ARM. The Avalon specifications are published by Altera and are relatively simple to implement. The document explains implemented signals with use cases and waveforms. The AXI interface is much more complex and tuned for throughput. ARM publishes information regarding that in the protocol specification document. Platform Designer supports both, and communication across interfaces are automatically handled. For example, you can have AXE manager talking to an Avalon agent or an Avalon host talking to an AXE subordinate. The decision of which standard to use is completely up to you and your situation. If you already have IP that conform to those specifications, you can continue using those standards. If you want something simple, then Avalon is the answer. But if you would like to implement complex interfaces that include security, then AXE is the way to go. Before custom components can be instantiated in Platform Designer, you'll need to create them. The easiest way to do this is using the component editor. In the component editor, you specify the HDL that pertains to your component. You can also specify the instantiation parameters that usually correspond to Verilog parameters or VHDL generic. This way, every instance can be different, making your IP more reusable. But the most important task of the component editor is to map the HDL ports to standard interface types and signals, and then define the property of the interfaces. Once the interfaces are known to Platform Designer, it can connect it to other components with the necessary components needed to bridge the interfaces. One final note on custom components. When creating a custom component, you should consider adding a System View Description or SVD file. This describes the register set of your custom FPGA peripheral to the ARM Development Studio or Ashling RISC-free IDE for Altera FPGAs, allowing the debugger to view and change custom IP in the FPGA fabric. This XML formatted file is available for off-the-shelf Altera IPs and could be created for custom components to allow self-documenting easy debug. Now that we understand Quartus Prime software and Platform Designer tool flow, let's look at SoC hardware system debug. We'll start with functional simulation. To make verification of custom IPs easy, Platform Designer supports bus functional models for both AXI and Avalon interfaces. Bus functional models allow for easy simulation of components by abstracting away the signals of the interfaces and allowing you to issue commands and responses to a design under test through a software-like application programming interface. You can use the BFM to see if an interface conforms to the protocol specifications, as well as to test the functionality of the interface. AFI BFMs can also be used to simulate the HPS AXI bridges. Avalon BFMs are available from Altera to test Avalon component interfaces. With BFMs, you can rapidly verify your FPGA IP because it's quick to instantiate various BFMs for each interface and test them through the given API. To simulate an HPS system, follow the steps here. First, create the system. Then, when generating the system, set to generate either simulation model or test bench system. When generating for simulation model, a model of the system will be generated. When generating a test bench system, a model of the system will be generated in addition to BFMs for any interfaces that are exported. Then generate the simulation model or test bench system. Lastly, create and run simulation script for your chosen simulator. You can use these steps to test both individual components as well as an entire system. If you want to learn more about the different supported simulators, you can go to the Hard Processor System Component Reference Manual for each Altera SoC FPGA device, or visit the Resources section on this presentation. In this manual, you can also find the links to examples for designs to simulate and get started with. To test an individual component, first create a Platform Designer system that has the component interfaces exported. Then when you generate a test bench system, clock, reset, agent, and host BFMs will be inserted automatically for you. If you're testing a host interface, an agent BFM will be inserted that allows your test program to issue commands. Monitor BFMs can be used to watch traffic and do coverage and protocol checking, but they will need to be manually inserted into a platform designer system. If you're performing a system simulation, you can generate a system for test bench clock, reset, and conduit BFMs will be inserted to allow you to simulate the system as if it was interacting with outside components. Here you would control the BFM through the test program, and test program will be used to simulate input and outputs of the system through the conduit BFMs. The HPS component itself is too complex to be simulated. To set the HPS for simulation, add the component to the system in Platform Designer. Then configure the component based on the application needs by selecting or deselecting HPS FPGA interfaces. Then connect the HPS interfaces to other components in the system. The conduit interfaces need to have the correct role names and widths. The conduit interfaces are opposite in direction to what is shown in the HPS conduit interfaces table in the HPS System Component Reference Manual for each device. One example of a connection might be an FPGA to HP's AXI subordinate interface to an AXI or Avalon Memory Mapped Manager interface in another component in the system. On the Generation tab inside Platform Designer, several options regarding generation for simulation are available. First, you have the option to create only a simulation model for your system with either Verilog or VHDL. When doing this, you'll need to create a separate and custom test bench in order to exercise the simulation model. Alternatively, you can create a test bench system which includes the simulation model in addition to BFM, depending on your setting. If you choose standard, BFMs will be inserted for all exported interfaces. This is most useful for component testing. If you choose to create a simple system, only clock and reset BFMs will be added. This more suitable for system testing. For test benches, you also have the option to generate for either Verilog or VHDL. The following figure shows a test bench that uses an Avalon memory mapped monitor to test components with Avalon memory mapped interfaces. The monitor's Avalon memory mapped host interface is connected to a component's Avalon memory mapped agent interface. The test program communicates with the monitor. The test program can use the monitor's assertion checking and coverage groups to ensure that all legal parameter values for the design under test Avalon memory mapped interfaces are tested. The Avalon memory mapped monitor also includes a transaction collector feature to collect and monitor transaction status. You can find this and other applications in the Avalon Verification IP Suite User Guide document. Once the test program is created, you can modify, then run the simulation test scripts. When you use Platform Designer to generate for simulation, Platform Designer automatically generates scripts for major simulators. The scripts for each vendor will be located in the appropriate generated directory. The generated script will automatically set up simulation environment, create and compile device libraries and sources files, and run the simulation. You can, of course, modify the script to customize your simulation environment. The table shown has a list of supported simulators. Now let's talk about on-chip component debug. System Console is the tool inside the Quartus Prime software tools allowing you to perform low-level system debug of your Platform Designer components without the availability of software. Everything in System Console is very easy to use, and you can issue commands through a TCL interface. Debug can be done over any traditional debug interface, such as JTAG, USB, or even TCP/IP. System Console performs tests on debug-enabled Altera FPGA IP. Perform board bring up with finalized or partially complete designs. Debug transceiver links, memory interfaces, and Ethernet interfaces. You can automate runtime verification through scripting across multiple devices. Integrate your debug IP into the debug platform, and perform system verification with MATLAB. Once System Console launches, you should see these window panes. The System Explorer pane allows you to view a hierarchy of the System Console virtual file system in your design, which may include connections, designs, design instances, devices, and scripts. When you write scripts and specify the path where they are located in the environment settings of your operating system, you can then run the scripts from the System Explorer. The Tools pane allows launching tools that use the System Console framework or to enable GUI widgets created by your script. The Tickle Console pane allows running commands and Tickle scripts from within the System Console. You can also source Tickle scripts. Finally, the Messages pane displays messages generated when running tools within the System Console. System Console also provides the hardware debugging infrastructure to support operation and customization of debugging toolkits. Toolkits are small applications that you can use to perform system-level debug of such elements as external memory interfaces, Ethernet interfaces, PCI Express interfaces, transceiver PHY interfaces, and various other debugging functions. The Quartus Prime software includes the available system debugging toolkits. For advanced users, System Console also supports Tickle commands that allow you to define and operate your own custom toolkits, as System Console and Toolkit Tickle Command Reference Manual describes. System Console tasks are grouped by services. Each service is a collection of functions available to accomplish a certain type of tasks. Services may be associated with particular components, and most services and paths to compatible devices and IP are automatically discovered when System Console starts. There are several methods to launch the System Console tools. You can do so from Quartus Prime software main window from the Tools menu. Then go to System Debugging Tools, and you will find the System Console option. You can also enter from the Platform Designer Tools menu from the NEOS 5 command shell. If you're launching the tool from the command shell, simply type System Console. System Console services provide access to hardware modules that you instantiate in your FPGA. Services vary in the type of debug access they provide. The JTAG debug service allows you to check the state of clocks and resets within your design. The device service allows you to program a new soft into your FPGA. Use the byte stream service to communicate directly to the IP core that provides byte stream interfaces, such as the JTAG UART or the Avalon Streaming JTAG interface Intel FPGA IP. The monitor service type allows you to efficiently read from a large range of addresses at a regular interval. Finally, the dashboard service allows you to easily create widgets, such as buttons, dials, and charts that makes automation of tests easy. This slide displays the basic flow when opening and using services provided by the System Console inside Quartus Prime software. After ensuring that the necessary components are added to your system and your board is properly configured, launch System Console and it'll be ready for interactive usage. You then will need to find the service. This is done using the System Console commands. After locating your service, it's convenient to set a variable equal to it. Once the service is found, you can open the service using the variable defined in the previous step to perform debug operations with the service. When done, you can close the service. The main view in System Console allows you to visualize certain parameter values of the IP that the toolkit targets. These parameter values can be static values from compile time parameterization or dynamic values read from the hardware, like reading from control and status registers, at runtime. The main view GUI controls allow you to control or configure the IP on the hardware. The Auto-Sweep view allows you to sweep over IP parameters to find the best combination and define your own quality metrics for a given Auto-Sweep run. This view allows you to sweep such a complex system when the multiple devices are visible to System Console. You can select the quality metrics from instances different from those you sweep. The dashboard view allows you to visualize the changes to toolkit parameters over time. It provides options to view a line chart, histogram, pie chart, or bar graph, and a data history. There is no limit imposed on the number of instances of the dashboard view open at once. The System Console Eye Viewer allows you to configure, run, and render eye scans. This feature allows independent control of the eye for each transceiver instance. The idea of FPGA adaptive debugging is allowing you to synchronize debug actions on the HPS with those on the FPGA side, including the signal tap logic analyzer. This is done through the use of standard ARM-provided core site compatible IP in the HPS. For software development, you can run, step, pause your code across a JTAG connection. With the previously discussed SVD files, you'll be able to change and view HPS and FPGA status and control registers directly in the debugger. You'll be able to cross-trigger from FPGA to HPS, which means a hardware signal or signal tap logic analyzer can trigger out and break HPS execution. Or you can perform HPS to FPGA cross-trigger where the breaking of code execution in the HPS through breakpoints, for example, will act as an input trigger for the signal tap logic analyzer or other hardware signals and FPGA cross-trigger, where the breaking of code execution in the HPS through breakpoints, for example. Finally, you can correlate hardware events with the HPS trace stream without breaking processor execution through events. FPGA to HPS cross-trigger and HPS to FPGA cross-trigger are supported. Core site systems provide all the infrastructure you require to debug, monitor, and optimize the performance of a complete HPS design and user logic implemented in the FPGA fabric. The debug system design incorporates ARM core site components. Core site technology addresses the requirement for a multi-core debug and trace solution with high bandwidth for whole systems beyond the processor core. Trace ATB connection to the FPGA fabric is provided to allow trace resources implemented within the fabric access to core site trace infrastructure within the HPS. ARM Development Studio for Intel SoC FPGA is license managed and available with a paid license. It supports all ARM processor subsystems in Altera SoC FPGAs and provides exceptional bare metal debug and trace capabilities. This is a development and debugging environment based on the open source Eclipse tools and gives you the ability to edit files, manage projects, and see various information through different perspectives, such as the C++ perspective or debugging perspectives. Ashling RISC-free IDE is an Eclipse C++ development toolkit-based integrated development environment, IDE, for Altera FPGAs, ARM-based hard processor system, and RISC-V-based Neos 5 processors. The RISC-free IDE provides a complete, seamless environment for C and C++ software development. You can use it to enable breakpoints, multi-core debugging, processor system debug with ARM HPS projects. For more information, you can visit the landing page and user guide on the subject provided in the resources section. To use the cross-trigger or hardware events feature with custom hardware logic in the FPGA, You can enable these options when instantiating the HPS component in Platform Designer. Once the HPS is instantiated, connect the ports to the logic you want. The Signal Tap Logic Analyzer emulates many of the features of an external logic analyzer. It taps signals within your design, meaning it samples, captures, and stores on-chip internal signal data values. This is done on the rising edge of a specified sampling clock. Signal Tap gives you the unique ability to monitor deeply buried design signals in real time during normal system operation. You're able to control and view captured data on the fly through a standard JTAG connection, typically used for programming the device, or, in some cases, remotely over a network. The Signal Tap Embedded Logic Analyzer, or ELA, is available for free and included automatically with a standard installation of the Lite, Standard, or Pro editions of the software. A version of the Signal Tap Control interface is also included with the standalone programming software, allowing you to control and monitor the ELA without a full installation of the Altera Quartus Prime software, though without the ability to reconfigure its settings. You can find this at the Altera FPGA Download Center. The logic analyzer is created in the target device using unused logic elements and memory blocks. To illustrate how it is implemented, here is an FPGA device programmed with a design. Multiple instances of the Signal Tap Logic Analyzer are added to the design, each with its own buffer built from available device memory blocks for storing captured signal data. Each instance is configured to tap desired signal nodes for monitoring or for defining trigger conditions. The JTAG connection programs the device as well as controls the operation of the signal tap instances after device programming. The logic analyzer can interface with other components or external devices. With the trigger in option, an external signal can be fed into the logic analyzer to act as a trigger condition. This signal can come from an I/O pin set in the pin planner, another instance of the ELA, an internal signal node, or the hard processor system of an SoC device. The trigger-in signal behaves like trigger condition 0, meaning that it is evaluated first and must occur before any other trigger conditions. You can set the pattern for the input trigger signal in the same way as a basic trigger condition using the pattern option. Enabling the trigger out feature sends an active high or active low signal to another component or device. The trigger out signal can be sent to an I/O pin to be placed in the pin planner, the trigger in another instance of the ELA, or the debugging hardware of the HPS. Sending the trigger out to the HPS is used to break code execution during debugging of the ARM processor or as a system event that gets inserted into the HPS program trace. The latency delay field at the bottom of the trigger out section indicates how many clock cycles are required before signals coming into the logic analyzer instance generate the trigger out signal. This value, calculated automatically as the logic analyzer is configured, includes all delays to the signal tapped instance. Here's a summary of the SoC hardware design flow again. You start with the Quartus Prime software project and set it to compile for one of the SoC devices. Then within Platform Designer, create a system, add, configure, and connect components, including the HPS, custom IP, or other off-the-shelf IP. Finally, generate the Platform Designer system, which include HDL files of the system along with other files such as software handoff files. After generation, you can perform functional simulation of components and interfaces using Avalon or Axed BFMs, or instantiate the system in your Quartus Prime software project in order to compile it. You'll need to run analysis and elaboration first, then make the appropriate I/O assignments, and finally perform a full compile of the design to create the FPGA programming bitstream necessary for on-chip hardware debug and release using the debug tools suggested. To learn more about simulating SoC systems in Platform Designer, feel free to read the Verification IP user guides. The Cordis Prime Software Handbook has a Platform Designer chapter that talks about the different generation features. Altera SoC FPGAs device handbooks also contain information on how to simulate the HPS. Lastly, we offer the Intro to Platform Designer, as well as the Advanced Platform Designer e-learnings that have detailed information on how to use the BFMs, as well as several relevant free online training. Thanks again for attending the SoC Hardware Flow online training.